Hello folks and welcome to Simplifying Radicals. You need your notes. If you have your flip chart, let's use your flip chart. If you're not using a flip chart, just your regular notes. You'll need a pencil, a calculator, and your perfect roots table, that yellow sheet that you have all those squares, cubes, fourths, and fifth powers on. Okay, so let's get started. So if you're using the flip chart, we are on the second day of 6.2 where we are going to learn how to simplify radicals. Okay, and you're going to flip up this tab, and on the inside at the top you are going to write know your perfect roots. You are going to write examples without variables. That's where all the examples where we do not have x's or y's in them go. And then the bottom part is where we will put our examples with variables. And it's important that you write assuming that they are all positive, because we are going to say that all the variables that we work with are going to be positive. All right, so let's get started. Before we do though, you need to have that perfect roots table, that yellow sheet out and handy so that we can reference it. All right, we're going to start by simplifying variables, number 1 and number 2. There are actually 4 of these problems, so make sure you have enough room for 4 of them. Now we have simplified square roots before. Remember, we've used the rule that says I can break down the square root of 40 into 2 parts. Okay? Well, I can find 2 things that make the square root of 40. Well, you know, there's a lot of things that make the square root of 40, like 2 and 20, and 8 and 5, and 4 and 10. But remember, what we were always focused on is that if this was a 2, that meant square root, and we were always looking for a perfect square that would divide evenly into 40. Now if I look at 2 and 20, 2 isn't a perfect square, 20 isn't a perfect square. That doesn't really work. 8 and 5, 8 isn't a perfect square, 5 isn't a perfect square, so that's not going to work. So remember that when we were talking about a square root, we were looking for a perfect square that divided into 40. Well, I think I found one. The square root of 40 would be the square root of 4 times the square root of 10. The square root of 4 becomes 2, and the square root of 10 cannot be broken down because that makes a decimal, so we leave it as the square root of 10. So this would be 2 square roots of 10. When I am simplifying radicals and I don't want decimals, I have to make sure that I leave in radical form. Okay? This says the cube root of 40. Okay, so now what I want to do is I want to go back to that table and I want to look at the perfect cubes column. And I want to find one of these perfect cubes that divides into 40 evenly. So what I would do is I would just start dividing 40 by all the cubes. Well, the first one's 1, and that doesn't really help us. But the second one is the cube root of 8 and the cube root of 5. Now notice my index has to be here. I can't write it like I did over here with the square root of 8 and the square root of 5 because I'm not talking about square roots. I'm talking about cube roots now. And the index is super important. So I can say this is the same as the cube root of 8 times the cube root of 5. And if we go back to that sheet, the cube root of 8 is 2. Okay? So it would be 2, because the cube root of 8 is 2, and then it would be times the cube root of 5, because that doesn't break down. Okay, so it's really important that I have my handy dandy root sheet available. Okay, here's example number 3 and number 4. These are the last 2 examples where we're simplifying our radicals without variables. This is the cube root of 72 So again, I'm looking for 2 cube roots that multiply to make 72, but one of them is a perfect cube. So again, I'm going to go back to my perfect roots table, and I'm going to say 72, and I'm just going to start dividing 72 by my perfect cubes. Well, again, 8 goes into 72 9 times, and the cube root of 8 is 2, and the cube root of 9 cannot be done, so we leave it as the cube root of 9. Again, that index is a cube root, and it's very important that it keeps coming down and finally is there at the end as well. If you leave it off, then it would say the square root of 9, and it's not a square root, it's a cube root. All right, this one is a fourth root. So when I'm looking at my table, I want to look for the fourth roots. And I want to see if there's any fourth power that divides into 512 evenly. So I'm going to just start dividing 512 by all that whole column. So let's start with 512 divided by 16. Well, it works, but what we have to be careful is that even though it works, it's not the largest one. So we want to keep looking until we find a better one. So as we go down the chart, you're going to notice that 256, the fourth root of 256 times the fourth root of 2 is the largest perfect fourth root. Okay, you want the largest. And the fourth root of 256 is 4, and the fourth root of 2 can't be broken down. So I leave it as the fourth root of 2. All right, so there's 4 examples without variables. Now we want to look at some examples with variables. So this goes on the bottom part, and we are going to assume that all our variables are positive. Okay, so there are 4 examples. Let's take a look at this one. Now, what I tell students is that when I have variables, I'm really not doing much different things. It's still the same idea. So what I do is, because the radicand has more than one thing, I split up the radicand as if I were going to do the numbers like I just did and the variables on their own. All right, so this says the fourth root of 625 times the fourth root of x to the fourth. Now, I want the fourth root of 625, so I go to my sheet and looky there. The fourth root of 625 is a perfect root, and that is 5. So that becomes 5. And then this is radical notation. So what I tell my students is to convert it to rational. Now remember, rational is the power is the numerator and the denominator is the index. Well, do you know that 4 divided by 4 is actually 1? And so 4 divides into 4 one time. So the answer is really 5x. Okay, well, let's try this one. Break it apart. Cube root of 64, cube root of y to the 6. All right, the cube root of 64, if we're looking at our sheet, that happens to be a perfect cube. That is a 4. Rewrite this in rational notation. And 6 divided by 3 is 2. And so this would be 4y squared. All right, let's try a couple more. I'm going to make them a little bit more complicated. But again, we want to assume that all variables are positive. All right, now this has 3 things. So all I do is split it up into 3 parts. Each of these are a radicand, and the product rule of radicals says that I can break up all of these into separate radicands. This says the fifth root of 4. Well, if you look at your fifth root column, the fifth root of 4 is not possible, so it stays the fifth root of 4. The fifth root of a to the 10th, I'm going to rewrite that as a 10 over 5, and I'm going to write this one as b 6 over 5. Now, 10 divided by 5 is 2, and so a squared is actually going to go out in front of my answer. So I'm going to write my answer down here, and I'm going to put this a squared out in front because it's not in the radical anymore. The denominator is 1, and if the index is 1, there's no such thing as a 1 root. Okay, there's a square root and a cube root, but there isn't a first root. So if the denominator is 1, then it just goes out in front. Okay, now this one's a little bit more complicated. So we have to think about this one. Now you just got done learning about simplifying exponents. So I'm going to ask you a really tough question. Is b to the 5 over 5 times b to 1 over 5 the same thing as b to the 6/5? And I'm hoping you're going to say, yes, Mrs. Brendan, that is definitely the same, because when the bases are the same, we can add exponents. And 5/5 plus 1/5 give me 6/5. Now, you're probably saying, well, how's that going to help me, Mrs. Brendan? Well, how that's going to help you is that you know that 5 divided by 5 is 1. And so that b to the power of 1 is going to go out here in front. But the b to the 1/5, if I were to rewrite that in radical notation, wouldn't that say the 5th root of b? And so this extra b that's left over is going to go right down here underneath the radical with the 4. And that becomes my answer. Now these seem to be a little bit more complicated, and they are, but if you think about all the things we've done and critically think about them, I think you can make it through these. All right, let's start with this one. The cube root of 54 breaks up, and so does the cube root of x to the 7th. Now the cube root of 54, I'm thinking, is going to be able to break that down by the cube root of 27 and the cube root of 2. The cube root of 27 happens to be 3, and the cube root of 2 stays the cube root of 2. Now I'm going to talk about the cube root of x to the 7th. Let's rewrite that in rational, which would be 7 over 3. Now, again, if we think about our exponent rules, isn't that the same thing as x to the 6th over 3 times x to the 1 over 3? Adding those exponents, I would get 7/3. And it just so happens that 6 divided by 3 is a nice even integer here, positive integer. X squared goes out in front. X to the 1/3 is the same thing as the cube root of x, and so then that goes down below. So there is the answer for this one. It would be 3x squared times the cube root of 2x. Now I know these seem to be a little bit complicated, but if you know how to go from radical to rational, that will help you. If you know your exponent rules, that will help you. And if you have your yellow roots chart in front of you, that will also help you. So there's some things that are kind of important for us to be able to be successful with these. And it's a lot of prior knowledge coming together in order for us to be successful. So hopefully tomorrow when you come to class, we'll be able to have that success in knowing what you're doing. We'll see you tomorrow.